I am pleased to welcome the host of the Wright Lectures, Dr. Eric Chason. Dr. Chason, besides being a character, is the director of the H. Dudley Wright Center for Innovative Science Education at Tufts University, where he is also research professor of physics and astronomy and research professor of education. He is an associate of the Harvard College Observatory, where he teaches introductory astrophysics, and is also affiliate director of the Massachusetts Space Grant Consortium at MIT. In addition, Dr. Chason has served on the Museum of Science's Board of Overseers since 2002, and he has a new book coming out next month entitled Epic Evolution. So keep your eyes peeled for it in bookstores next month. Please join me in welcoming Dr. Eric Chason.
Thanks, Lisa. Okay, well, thank you very much. Thank you, Lisa, to your staff and to the other members of the Museum of Science. This is a wonderful partnership with the museum between the Museum of Science here in Boston and La Fondation Wright de Genève in Switzerland. This is a series that runs annually in the odd year in Boston and the even year in Geneva and other European capitals. We're transmitting tonight out onto the web as well, and so we'll welcome those people as well. But we've not quite yet figured out a way, I guess, in which webcast viewers can ask questions. But maybe next week we can take that next innovative step and involve them in our panel discussion. So the topic, as is usually the case here on this side of the Atlantic, is cosmic evolution. It's the story that I'm passionate about. It's a story about ourselves. It's not an anthropocentric story necessarily, but it's a story about how changes throughout the entire history of the universe, all space and all time, among galaxies, stars, planets, and life form, have produced us. As Phil Morrison used to say, hydrogen is a light, odorless gas, which, given enough time, changes into people. Basically, that's the story we're trying to tell here, but we're trying to tell it from a scientific point of view by placing some empirical data on the table and some testable ideas, testable propositions in the world of science. And basically what we're trying to do here is to present a coherent, integrated, interdisciplinary tour across so many of the natural sciences, starting as we did last week with physics and astronomy, moving through geology and chemistry, biology, up through anthropology. It's a story in which we're trying to create, in effect, a cosmology in which life has a position, maybe even a role to play. Last week we brought before you, along the arrow of time, two outstanding world-class scientists, as you noted if you were here. Frank Wilczek led off with a discussion of the early universe, took us back astonishingly close to the Big Bang, well within the first second of the Big Bang, and followed by Colin Norman of the Space Telescope Institute down in Baltimore at Johns Hopkins, who told us about perhaps work that he's doing on what I consider to be the greatest missing link in all of cosmic evolution, the origin of galaxies. Even more so for the origin of galaxies than for perhaps the origin of life or the origin of intelligence that we will discuss in subsequent weeks. In fact, next week we will have the transition from the animate world to the inanimate world. Lynn Rothschild will be here with us, an astrobiologist from NASA Ames in San Francisco, talking about chemical evolution, those pre-biological steps that led to life. And Jim Henkin will be here as director of the MCZ at Harvard, talking about more advanced forms of life and how the arrow of time moved us naturally, perhaps even inevitably, toward greater complexity, as we moved across that arrow of time from simplicity to complexity, from inorganic to organic, from chaos in that old-fashioned Greek sense to order. With the wonder, how is there so much order in the universe? And that order will be exemplified again in our final evening, the fourth in this series, 2 weeks from tonight, when Fred Speer will be here from Amsterdam, a world historian and anthropologist, to tell us about how we have arrived at the here and the now, with all the complexity we see around us from an anthropological point of view. And then the eighth speaker, 8 epochs, 8 speakers, will be a person who will make kind of a gesture to the unknown. Jill Tarter will be here. She's leading the effort, the United States effort to search for extraterrestrial intelligence, a subject thus far for which there are no data, but it is an expression of where this arrow of time may be headed, where we may be headed in the future if there be other aliens out there. And she will have some speculation on those issues as the final speaker. Tonight we have two wonderful speakers in the intermediate or early stages, the stellar and planetary epochs. If we have trouble with galactic origins and evolution, we have a whole lot less trouble with stellar origins and evolution. If galactic evolution is a missing link in cosmic evolution, stellar evolution that we talk about tonight is one of the strengths of cosmic evolution. And we're pleased to have as our first speaker tonight an expert on stellar evolution. Michael Shara is an astronomer, an astrophysicist, currently a curator in charge of the American Museum of Natural History in New York City. That's where the wonderful Rose Center for Earth and Space is located, as we view it from this location here in Boston as the other Hayden. And Michael also is an adjunct professor of astronomy across the way at Columbia University. I first met him at Space Telescope again back in Baltimore in the 80s when I realized he was not only a world-class scientist but also a very strong explicator and teacher of science for students, for the general public, hence the reason we've invited him here tonight. He took his PhD at Tel Aviv University with regard to interactions and collisions among stars in very dense star clusters. And currently he and his group are trying to literally inventory or weigh all of the 100,000 nearby stars in our part of the suburbs of the galaxy. So please welcome as our first speaker, Mike Shara from New York City.
No. Now you can. Well, you may say to yourself, stars, planets, birth, evolution, death. Okay, those are reasonable topics for an astrophysicist to talk about, but what kind of conceit is this? He's going to tell us about sociology. Give me a break. Well, of course, I mean stellar sociology. And believe it or not, there is, in a sense, that kind of subject. And what I'm going to do really is play foil. I'm going to set some of the groundwork for the stuff that the next speaker, Dimitar Sasselov, is going to tell you about planets by basically telling you where the carbon in your muscles and the iron in your blood comes from, via stellar evolution, of course. But then I'm going to take 5 minutes afterwards to play agent provocateur in rather more detail. What happens when stars don't live by themselves, but when they live in societies? And just as a human being living off in isolation will be very different from a human being being studied in a crowd, so stars and crowds are very, very different. These are the things that I would like to try and cover tonight, perhaps a little too much material, but we'll see how it goes. Where do stars come from? And, of course, where do planets come from? They're born together. There's an intimate connection between the two. Where do the chemical elements come from? Because if there were no iron, there would be no iron core or nickel core to the Earth. There would be no Earth and possibly, very likely, in fact, no life in the universe, certainly no terrestrial planets, no place for us to have evolved. And then I want to tell you a little bit about the death of stars, but also the rebirth, because stars are like phoenixes. At the end of their lifetimes, as they die, their ashes get recycled back into the universe. Afterwards, I'll tell you a little bit about stars in star clusters, where they behave very differently from stars in the field. What happens when two stars actually whack into each other? Up to about 15 or 20 years ago, it was a ludicrous question even to ask, because astrophysicists believe that the density of stars in the universe is just too low. Stars never run into each other. The sun will never encounter another star, never run head-on into another star. But there are dense places where these things happen. And finally, I want to tell you about stellar promiscuity. I hope there's nobody under 17 in the what happens when stars do very naughty things to each other? Here's some observational data. If you don't know anything about where stars or planets come from, you're confronted with some basic observational facts. All of the planets in the solar system are going in the same direction. Okay? It's as if somehow Mercury, Venus, the Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, I don't include Pluto. Pluto is not a planet. All of the 8 planets of the solar system go in the same direction around the sun. Not only do they go in the same direction, not only do they orbit in the same direction, but they spin in the same direction. So their orbital and spin angular momenta are aligned. That's a fancy way of saying they're all going in the same direction. Okay, that's one basic observational fact. And any theory that purports to explain where the solar system or where the stars or the sun comes from has to be able to explain that at the same time. That's a critically important piece of data. Here's another one, and that is the planes of the orbits are also the same. That's an astonishing coincidence, if it's a coincidence. Why aren't the planes tipped at 80 or 90 or 70 degrees to each other? You do see that Pluto is in a different plane, but I don't have to explain that because, again, Pluto is not a planet. planets are really stellar after birth. That's the bottom line. If you take a very large cloud of hydrogen, yes, it does turn into people. There are some intermediate steps, a few along the way, and one of those intermediate steps is that most of the stuff falls into the big central mass. The big central mass picks up more and more mass, acquires more and more gravity, and goes giant sucking sound, and most of the material falls in to become the star. Conservation of angular momentum, conservation of spin, just like the skater pulling in her arms at the Olympics, spins faster and faster, and also provides the kind of support you need to make a torus, a donut, a bagel, a disk, all the same word. That's the plane of the solar system, and that's why everybody is going in the same direction. So that's the picture, basically, that astrophysicists have in not even 0th approximation, but -1th approximation. The crudest of the crude of the crude approximations is that stuff falls in to form the protostar, and the stuff that's left behind makes the planets orbiting a star. Now, if that's true, if what I just told you isn't complete science fiction or utter fantasy, then most stars should make planets. Planets should not be unusual. On the contrary, stars in general should have planets. And you should really think of galaxies, 100 billion stars or so, as being planet factories. That's the business of a galaxy. It's a place that makes new worlds via this process. Well, once you've made the disk doesn't just sit there. All sorts of funny cohesive forces, electromagnetic forces, various others take over and make little grains of dust and ices and what have you. And after you wave your magic astrophysical hands for 1 million or 2 years, little pieces build up into bigger and bigger pieces, and you get agglomeration. You go from the left to the right, and you sweep up the inner and outer material of the solar system to form the planets. You make two kinds of planets. You make the rocky iron-nickel planets in the center, okay, the Earths, the Venus, the Mercury, the Mars, and all the hydrogen and the helium leaves because the sun is too hot. And in the outer part of the solar system, you also make Earths, except the hydrogen stays behind, so the heavy stuff settles to the center, the light stuff is on the outside, you make Jupiters, okay? That's the way we all thought it was, and that's the way we all thought all planets were made until about the mid-1990s, when we got a rude awakening. And we're going to hear more about that in the next talk. Now, what happens if you don't make planets? If you decide that you're going to be really obstinate, you're a star, and you say, I don't want to make planets with me, well, you have a problem. You have an angular momentum problem. You have a spin problem. And the brightest star in the constellation Leo, otherwise known as Alpha Leo or Regulus, has chosen, in all likelihood, not to make planets, or at least not to make planets the way we have. That's what Alpha Leo looks like. It looks like that football. There's an actual interferometer image, a real picture of that star, and it looks like a football. It's not round like our sun is at the bottom. We always used to think that all stars are nearly perfect spheres. Well, there's an excellent example of a star that most certainly is not. That's what happens if you drag in all of your angular momentum. It turns out that in the solar system, all of the mass, that is 99.9% of the mass, or 99.8% of the mass is in the sun. But 98% of the spin, the angular momentum, is in Jupiter. It's not in the sun. But if you leave the angular momentum behind, that's what you get. Where are stars born? Here's a stellar nursery, sometimes called the Eagle Nebula. The eagle is right in the center. It's those three fingers poking up towards the left. Can you see an eagle? Depends on how much Cabernet Sauvignon you've had for dinner. Some of you may see an eagle. Let's zoom in on the eagle. There's a very famous picture taken by the Hubble Space Telescope. Those are the three fingers. So a highly magnified and exquisite resolution view of the Eagle Nebula, otherwise known as M16. And what you have here is a place where thousands of stars are being born in those dark columns of carbonaceous and silicaceous material. What you also have is a couple of very bright stars up at the top. And those spotlights, those very bright stars, are evaporating away the tops of those columns. That's the glow you see at the top of each column. And little tiny fingers seem to be sticking out. And those little tiny fingers are places where newborn stars are emerging. Think of new stars as pecking away at the shells of the other new stars and letting out those embryos. So star formation and the process of making stars and the new stars themselves are intimately linked. New stars are affecting the embryonic stars by helping to free them from their gas wombs. Here is a womb, if you will, otherwise known as a giant molecular cloud with the prosaic name of Barnard 68. It looks like a kind of ink blotch sitting on the cosmos, many, many thousands of stars in the Milky Way in this dark region. Of course, what you're seeing is lots and lots of grains of carbon and silicon and carbon monoxide molecules and all sorts of other stuff that is starting to collapse under its own weight. And we think that this is the earliest stage of a star. If you compare the birth of a star to the 9 months of pregnancy, this is something like the first or second week of gestation. Now, significantly later on, really around the time of birth, you hear some of the howls of birth, and those howls are accompanied by jets of material. Just as babies eject material at high speed from various orifices, so young stars eject material in jets. And here you have one of them. The reddish blob at the bottom is where you have a baby star, not yet emerged from its cocoon of enshrouding material, and that jet of material that is being flipped upwards at very high speed is telling us that there's still a lot of activity going on, material still infalling into that baby star. Now here's a whole nursery, many thousands of stars. It's the Orion cluster. If you look in the constellation Orion in the winter sky, Orion's sword is this funny little glowing thing. A close-up picture reveals many, many thousands of stars, and those stars, insofar as we can measure, especially with the Hubble telescope and other very sophisticated instruments, those stars are always born with disks. There's always material around those stars. Here's a close-up of one of them taken by the Hubble telescope. The embryonic star is the reddish dot at the center. The dark material is the leftover detritus, the stuff that isn't accreted into the star and that is going to form into 1 or 2 or 3 or 4, maybe 8 or maybe 15 or 20 planets. That's the material left over that's going to make a solar system. Now, what really is a star? How do you define a star? Probably the simplest definition is bound by self-gravity, held together, obviously an astronomical body, but held together by self-gravity with an internal energy source. Most stars are spherical. Well, we used to think that way until we got that picture of Alpha Leo, and now we're beginning to rethink that one. Stars are usually nuclear powered. The sun is a hydrogen bomb. Nothing more, nothing less. The reason it doesn't explode is because there's enough gravity to hold it together. That's why it doesn't blow up. But there are nuclear reactions in the core that I'll describe in just a minute or two that power the sun and most other stars. But it can also be a gravitationally powered object. That is, it can have run out of nuclear fuel and pulling itself into an ever denser state, giving up energy in the process. Or it can be an object that's just plain hot with lots of leftover heat. It can be a dead star now, something called a white dwarf star, gradually radiating its energy out into space. The other thing to point out here is that there is a boundary between stars and planets that is in some sense fuzzy. Now, it's certainly true that nuclear-powered stars are different from non-nuclear-powered stars. There's a magic number, about 7% the mass of the sun. And if you cross that mass, you become a nuclear-powered star. And if you don't cross that mass, you're something else. But that something else is fuzzy. It's not really a star, and it's not really a planet. It's something that astrophysicists refer to as brown dwarfs or failed stars. The yellow sphere, or that piece of the yellow sphere on the left, is the sun, a G2 dwarf star. 6,000 degrees Kelvin is its surface temperature, 1,000 times the mass of Jupiter. That's a nice, average, run-of-the-mill star. Happens to be very close to us, only 8 light minutes away, which is why it's so bright. Now, if you shrink the mass of the sun down to only 75 times the mass of Jupiter, you still have an object that is a star. It's going to generate nuclear reactions in its core, albeit tens of thousands of times more slowly, so the object will be much more faint. And that's called an M8 dwarf, and that's the end of the stellar sequence. If you drop from 75 to 65 Jupiter masses, nuclear reactions turn off. There is no nuclear furnace. It's as if you'd inserted those cadmium rods into the nuclear reactor, absorbed all the neutrons. Nothing is happening. That's because the temperature is just a little too low in the center of the object to generate nuclear reactions. Drop down to 30 times the mass of Jupiter, or down to the mass of Jupiter, and of course you still don't have a star, you have a planet. But notice something interesting. Look at the relative sizes of those objects. The object that's 75 times the mass of Jupiter is smaller than Jupiter. What's going on here? The relative sizes are all right. They're all correct here. Well, it turns out that the gravity of a 75 solar mass object is large enough to pull it into that very dense configuration. And the gravity of Jupiter isn't dense enough to pull it into something much, much smaller than Jupiter. The balance between pressure outwards from nuclear reactions and gravity inwards is what determines the size of that M8 dwarf and all stars. And it's an interesting coincidence that all of these objects turn out to have about the same size. Now, astrophysicists have in many ways solved the problem of the structure and evolution of single stars, stars living in isolation. By structure, I mean an image. You can take a snapshot of the sun at one point in time. By evolution, I mean a video of the sun. If you could have a video of the sun and know everything about the sun for its 12 billion year history, then you would know everything there is to know about the sun. That's the structure and the evolution. We understand full well that gravity and energy generation, that is gravity pulling everything inwards, energy generation pushing everything outwards, are the relevant things that we have to consider in the evolution of a star. And if you violate gravity, that is, if you somehow add in too much mass and support yourself with pressure, something terrible is going to happen to a star. Those are the main causes of death of stars, usually violent, usually very quick. A closely associated point with all of this is what is called nucleosynthesis, or the chemistry of the stars, and the chemistry of you. Where do the elements in your body come from? Well, we know that the hydrogen and the helium that we see in the universe came out of the Big Bang. These are natural consequences of the enormous explosion that created the universe. But the other 90 naturally occurring elements, well, there's actually a couple that are not really naturally occurring. They're not quite stable, but never mind. From lithium all the way on up to uranium, those are referred to by astronomers as the metals. Okay, we're not chemists, we're astrophysicists. There's hydrogen, there's helium, there's everything else. And the reason we do that, well, it's true. And the reason we do that is because hydrogen is about 71% of the mass of the universe, helium is about 27%. So the remainder, the Z, is only 2%. And near the sun, it's about 2% of the rest of the universe. And we see it in many, many stellar spectra. Now, it is true that there are stars we see which have much less Z. There's no iron, there's no nickel, there's no carbon, there's no nitrogen, or virtually none in some stars. And some stars have up to 3 times as much as the sun. Now, why is that true? And what does that tell us about the evolution of stars and life on Earth? Here are the basic principles, as I said, that control a star. Pressure and gravity. The dark blue is the weight. That is, dark blue arrows are the weight at any one point in the star. Those are always inwards. And the light green is outwards pressure generated by the star. For the vast majority of all stars, these two forces balance perfectly at every place in the star for all time during nuclear burning, because otherwise the star would either contract or expand. The sun is not contracting, not expanding, so it must be in hydrostatic equilibrium. The source of energy inside the sun in most stars for most of the time is hydrogen fusion. Starting from the left, 2 H1s, 2 protons crash into each other and release an 2H. That's a deuteron, deuterium nucleus. The deuterium nucleus instantly runs into a proton and creates a 3 helium, helium-3 nucleus, and 2 helium-3 nuclei crash into each other to make a helium-4 nucleus, with the release of energy and neutrinos and all sorts of other stuff. So there's nuclear transmutation going on. There's alchemy inside the core of the sun, changing from the light elements to the heavy elements with the release of energy. That's the secret of why the stars shine. Something that we really only understood as a species from the 1950s onwards. Okay? Nobody 2 centuries ago or a century ago could tell you why the stars shone, why the sun shines. Today we know the answer, and this is the essence of it. Now, stars face another problem. You generate lots and lots and lots of energy in your center. How do you get it out? Well, there are only 3 ways. You can conduct the heat, you can radiate the heat, or you can convect the heat. You can boil yourself. It turns out that most stars, for most of their lifetimes, take the second 2 paths. The sun radiates its energy from the surface, but it actually boils some of its heat from the inside. And different stars take these 2 routes in different proportions. Here's an average star, which has a radiative zone, that is photons or light, transmits most of the energy towards the surface. You may need to boil near the surface for various technical reasons. That's how you move energy through it. If you now say, okay, I can write down the equations which govern the evolution of a star. Those are the equations in the bottom left corner. There's a pop quiz at the end, so you'd better write them down quickly. You stuff them into a computer with the appropriate boundary conditions, and that table up there, full of numbers, actually describes the sun. The first column is R over R sun. The bottom number is 0. That is the center of the sun. The top number is 1. That's the surface of the sun. So go right down to the bottom of the column there where it says 0, and now go to the right. You see 14.62. 14.62 is the temperature at the center of the sun in millions of degrees. 14.62 million degrees. Actually, it's a little bit hotter. We think it's closer to 15 or 16 million. The density at the center of the sun is about 134 grams per cubic centimeter, and the amount of mass in the central point of the sun, by definition, is 0, as is the luminosity. But then as you move out, say to 10%, that is the one line up from the bottom of that table, you see the temperature of the sun has dropped to 12 million degrees. The density has dropped to 85 grams per cc, and so on and so forth. This is a kind of slice through the sun, or a kind of simple description of the pressure, the temperature, the density, and astrophysicists can also tell you the chemical composition, the velocity of the material, and so on throughout a star, throughout the sun, throughout its lifetime. This is the evolution of a star. When we do this kind of exercise, what we find is we can predict things. We can predict what the sun is going to be like in another 4 or 5 billion years. The sun today is that little yellow dot on the left. 4 billion years from now, the sun will be a red giant, 100 times bigger than it is today, because it will have exhausted its supply of hydrogen. No more fuel, no more food, no more pressure. Gravity is going to condense the inner part of the star. That releases a lot of energy, causes the outer part of the star to expand. The sun will get big enough to swallow Mercury, Venus, and the Earth. It will boil away the atmosphere, the oceans, and cause the Earth to spiral into the sun, to crash into the core, to be consumed. And on that light note, I should probably stop, but I won't. Here's a cluster of very young stars, stars that we think are only 40 or 50 million years old, the Pleiades. It's a group of several hundred stars moving through space. The blue fuzz used to be thought of as embryonic material left over from the formation of the stars. It's not. The Pleiades, as a group, happens to be moving through a cloud of dust and gas, and that's just reflected light off some of the dust grains that we're seeing. These stars, though, were all born at around the same time, and they're all at about the same distance from the Earth. Here's an older cluster, and if you look really carefully, in the center of the cluster, you'll see one star that isn't the same color as all the others. Do you see that sort of ruddy, reddish star in the middle? Well, that star is a red giant. That happens to be the most massive star in the cluster, or it was a little time ago, and it is, if you will, observational proof of this theory that as star clusters get older, the most massive stars burn themselves out first and become red giant stars. Well, why are those stars important? It's for the following reason. The stuff in the center of the star that was hydrogen at the beginning gets transmuted into helium, and then the helium ignites in nuclear reactions and gets transmuted into carbon, oxygen, nitrogen, perhaps even some magnesium in the core of the sun. And then when the star becomes a red giant, it can start ejecting some of that material out into space. And here's a beautiful picture from the Hubble telescope of what I like to call a stellar phoenix. It's a star that's dying. This is what our own sun may look like 4 billion years from now. The sun would be the remnant of the star at the center, and the outer parts of the star have been ejected into the interstellar medium, carrying lots of oxygen, nitrogen, carbon with it to enrich the interstellar medium in these heavy elements, in future generations of these heavy elements for the next generation of stars. The heavy elements, on the other hand, the iron, the nickel, the gold, the copper, the zinc, all the way on up to uranium, come from stellar explosions like this, called supernovae. And if you ever ask the question, where do my gold earrings come from? Well, the answer is from objects like this. Objects more than, perhaps 8 or so times the mass of the sun end their lives in violent explosions called supernovae, which produce much of the, if not all of the heavy elements in the universe. And there is one. There's a supernova down at the bottom, a metal mine, as I refer to it. And it's fun to compare a supernova with an entire galaxy. 100 billion or so stars, and you can see the supernova shines about as brightly as the whole galaxy combined at its peak brightness. So a star right at the end of its lifetime will undergo a kind of collapse and explosion, ejecting huge amounts of heavy materials into the interstellar medium, which are going to end up in the cores of planets and in your bloodstream. That's where the iron in your blood comes from. That's where the calcium in your bones comes from. That's where the phosphorus in your DNA comes from. And that's where the iron-nickel cores of terrestrial planets come from. The dark stuff you see, the bands around that galaxy, are mostly carbon and silicon grains, the intermediate mass elements that are ejected from red giants in medium and low mass stars. So you have these two processes going on, mostly high mass stars producing the very heavy elements, mostly lower mass stars producing the intermediate mass elements. I want to introduce a different kind of cluster here. This is called a globular star cluster, and it's dated by several processes to be about 13 billion years old. It's almost as old as the universe itself. These star clusters are very poor in metals. I noted here that in this case, Z equals 0.002. It's only got 1/10 the metal content of the sun. Many globular clusters have 100th or even as little as 1,000th the metal content of the sun. And that's because they are very old. They come from the first or second generation, well, probably the second generation of stars. At the very beginning of the universe, when the first stars were forming, there couldn't have been metals. The Big Bang only made hydrogen and helium. So these clusters made out of very primitive material, very unprocessed material, have very little by way of metals. But metals may also mean very few planets. An exquisite search has been done for planets in this object with the Hubble telescope. It's pretty straightforward. You point the Hubble telescope at this thing and take a picture, then another one, and keep on doing that for 8 days, and look for eclipses. Look for Jupiters moving in front of their host stars. And the number expected, if the stars in 47 Tucanae had about the same number of planets that we might have expected in a typical star like the sun, we expected about 13 eclipses. 0 were found. That indicates that there are at least 10 times fewer planets in this kind of star cluster than there are in stars or around stars orbiting the sun. So the bottom line seems to be that metal-poor stars may have no planets. Metal-rich stars possibly do have planets, possibly have lots of planets, maybe in every case. It is the supernovae that enriched the subsequent generations of stars in metals and allowed planets and ultimately allowed us to exist. Now, we're going to do a little experiment here. Maybe. The finger came up. Fortunately, it's the index finger, and we're going to press this finger and see if we can show you a simulation of a globular star cluster. What happens if you put 100,000 stars next to each other? Well, it's a little bit like cramming 100,000 people into Times Square on New Year's Eve. They move, they jostle, and there they go. This is not an animation, this is a simulation. We have very high-powered special-purpose computer boards at the American Museum of Natural History and other places that allow you to do GMM over R squared, the force of gravity, acceleration, and follow the dynamics of stars in globular clusters. So you've just watched, or you are watching 10 million years in the lifetime of the globular cluster. The density of stars at the center of that globular cluster is so high that stars physically crash into each other. We've just flown through the globular cluster, or we've done a virtual flight through the globular cluster. Very pretty. What happens when two stars collide with each other? It's a legitimate question to ask. What happens to their evolution? What happens to them? Well, the stars have tremendous amounts of self-gravity. They are fluids, of course. They're like liquid drops, but they're controlled by gravity and nuclear reactions. Until about 15 years ago, we had no idea, but very sophisticated computer simulations now allow us to try it on a computer. What happens when two stars crash into each other, when stars really don't live in isolation, when they hit? And the answer is this. The blue lump, or the purple lump, is the smaller, denser star. The stars eventually merge. Again, sort of phoenix-like, to produce a more massive star called a blue straggler, which really is a brand new star because you've mixed fresh fuel into the core of the star. You've taken two ancient 13 billion-year-old stars, pressed the reset button, and turned them into a brand new baby star. That seems to be the answer. And of course, flung lots of materials out into interstellar space. And here is a picture of those teenagers in a retirement home. The globular cluster is the image taken by the Hubble telescope. The image on the right are the blue stragglers in the globular cluster 47 Tucanae. The ones circled in yellow are those very blue stars. So we actually have as close to proof, well, you can almost never prove anything in astrophysics, but we have stars that have no business being there in this very ancient star cluster, and we're pretty sure that they are caused, in fact, by stellar collision. I'm also going to talk a little bit later on about stellar promiscuity, but I want to sort of titillate you a little bit now just by leaving that up there for a minute and actually invite Eric to come up and introduce our next speaker.